let's start now. The structures, so these will be maybe slightly more open than the previous kind of book-based approach, the last remaining lectures we have. I had these on my own initiative, some of the crucial data structures, and we will start with hash tables, basically. We've been using them all the time, dictionaries in Python, hash tables, hash maps, also associative arrays, like PHP uses associative array, I believe it's called, right? I think also Lua. Right, so basically, it's the main big structure next to array-based structures, right? We all know we have a key. So why do we need them? Well, let's again look at Pigo cheat sheet, our friend, right? And we have array, right? We have O1 accessive, we have the index, but search, insertion, deletion is O n time, right? A hash table, well, it does not have such thing as a, not such an index. You have search by key, right? Insertion by key O1, deletion O1, right? So these are the good news, right? This is what we are trying to reach. That's why we want the hash table, right? The bad news is, of course, if you do it badly, you end up with this, basically, right? If you do badly, you end up with ON performance, right? And we are going to see how we can avoid it. But again, so first of all, so how would we, let's start, I guess, with the most easiest way you could think of hash table. Let's say you have an array, and your keys are numbers from 1 to 100, right? Well, then it's trivial, and you are storing something. Right? Those are the keys, and the values could be, let's say, strings or whatever, right? So let me draw this. Let me make a new picture. Right? So maybe I'll go draw something. Right? Where's my? Oh, there it is. Right. So your keys, right? Keys would be. Again, how many keys would be? Let's say 0, 1, 2, 3, 4, 5, right? And then you have maybe, I don't know, some strings or something, I guess, or numbers, let's say RBS, right? You have RDU, right? Valdis, and so on, right? Right. What else would say? Nose, right? Right. Something else, right? Test. Right? What's the last value? I don't know. Dumplings. Okay, awesome. All right. Dumplings, right? So, if your keys are numerical and they're in order, right, it's technically a hash table, but basically, how would we do this, right? I mean, we have numeric keys, right, and they start with 0. I mean, what do we use? What kind of structure can we use? They say this. I mean, okay, so yeah, obviously array, right? I mean, but why else would you want to use anything else, right? Because you have this 0, 1, 2, 3, 4, 5 keys. So technically, yeah, array, right? We use the array as these are the keys because guaranteed all one time, right? So array, right? So how would we say it? We basically probably use something like this. I would use array type structure, I guess. Right, array. Right, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right, so keys, right? Keys, keys would be 0, 1, 2, 3, 4, 5. Right. So how do we store these? Technically, how do we store them? How do we store? Well, we can't fit them immediately. Probably pointers or reference to the actual strings, right? So, and then of course, right, a pointer, or reference pointer or reference, depends how the language, right? And so, right, again, we get O1 performance, right? So this is all very nice, right? Right, pointers, So, it works perfectly, right? The only problem is, of course, the keys, you need, of course, so it has no semantic meaning, second key is Valdis, right? Obviously, also these keys are completely, not guaranteed in real life. You don't need, numeric keys are just not very useful, right? So you want to check whether game is novus, right? Not number 3 is novus, right? So, but this leads to the idea, right? How to implement hash tables, right? We can still use arrays, right? Almost almost all, I don't know actually, well, pretty much everything uses arrays underneath because arrays are awesome, right? We have caching, everything, performance, right? But we just need something, that's why they call cache tables. We need something to transfer, right? To transfer these keys, right? We need some sort of hash function. We need to transfer if you have, let's say, key is game, right? We need game, right? Key game, right? We need it transfer into 3, right? And then we go here, right? So we need some sort of hash function, right? Out of this, so this arrow is hash function here, right? So arrow is hash function. So hash function, hash function, right? Out of game, out comes 3, right? Okay. So in this case, it goes 3. Does this have to be 3? No, it doesn't have to be 3. But now we have the problem, right? So in theoretical world, right, we have an array. We know, if we know ahead of time that we are going to store specific values, we could come so-called perfect hash functions. You can say, okay, yeah, game, we always going to store game value in the 4th element, with index 3, and we have a hash function for game will give 3, and it's perfect basically, right? So there's no conflicts, no nothing, right? And RBS is always gonna, key school will give you 0, right? And key lector will give you Valdis, and so on and so on and so on, right? And key food will give you 5 and dumplings, right? So very good, but we usually don't know the keys, right? We want arbitrary keys, right? So we have some challenges basically. The biggest challenge, of course, is two challenges. Well, first of all, how do we get key? If assuming we have an array, right? How do we guarantee? Let's say we have some hash function. Hash functions generally give you a number, right? How could we fit this number inside these keys? What's the trick we could use? Like the last step of our hash function, or maybe like intermediate step? What could we do? But I'm recording this, I hope. Right? Hopefully everybody can hear this, right? So hopefully the mic picks up on this. Right, I don't know. Right, so any ideas? Okay, we'll get to this, I guess. I'll make a new picture, I guess. Right, keys. Right, so I'll save this as idea of hash function. Hash map, right, hash map, right. Okay, so for hash function, anybody has an idea? Okay, so I guess I'll make a new one, new paint job. Right, so we have some keys, right? The keys, let's assume for sake of this is going to be, okay, for now there'll be numeric keys, I can't spell, right, but they are, let's say integer 32, right? So int 32, so this means what? Let's say, okay, they are positive, okay, signed, okay, I mean unsigned, let's say unsigned. I'll make it easy for you for now, right? Unsigned, 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 sign, not sing, control, sign, come on, okay, one more, unsigned, right? So this means 0 to 4 billion something, right? 4 billion, right? Okay, right. But our hash table is going to be how big? Probably not 4 billion. We have a problem with that, right? We don't want to have this such big table, right? So we have hash table. Let's make it hash table. Hash table will be, I guess, only 256 values. Very tiny table. Only 256, right? 256, right? Right? Right. So 255 and 0, right? And assuming we're going to use pointers here, right? 1, 2, 3, right? And 254, right? Small to store, I don't know, 100 of them, right? You're going to have 100 keys. Well, let's say we have 100 keys, right? So 100 keys. So we have space, right? That's good. Right. So what do we do? How can we make them fit? These are keys, right? Values, we're not worrying. Values just going to be pointers, right? Values just pointers, right? So what's the idea? What's a simple idea? Like the simplest thing I could do. You want to fit them here, right? The keys. Because basically what you're trying to find, when I say fit, you want to find the index, right? From 0 to 155. What's the simple approach we use? I mean, that's like everywhere, right? And how do you make them fit? We have 4 billion values possible, but we only have 256 boxes.
Your question was how can we fit?
Yes, the keys. Basically, in comes. Let's say I want to find, let's say I have my structure, I'll call it HT or something, H table, right? Table, right? And I want to say get I don't know, 9001, right? Right. That's a key, right? This is a key. That's a key. And there's some, I don't know, could be a string afterwards, that's a pointer, but we don't worry about that right now. But, so 901, right? I want to get out the value, right? So, how do I map this 9001 to one of these indexes, right? I don't know which one yet, right? But one of them.
Divide by 256 and get what's left over?
Yes, of course. I mean, we take modules, right? Or the binder, right? So, we take a module. So, you got the idea. Yeah, and that is a basic idea. But, there's always a but, of course, right? It's not so simple. It would work, right? With some problems, right? Let's think about this, right? So it works, right? So yeah, so right, 256 in this case, right? All right, so that's good, but we have a problem, right? So let's say I'm trying, let's say I get 1024, right? Get 2048, right? Get 4096, right? Right. All right. So, what's going to happen with these?
They will return the same.
Yes, exactly. Very good. So, it's going to map to the same value, which is going to be in this case perfectly 0 to this first element. They all, right? So all three, right? All three, 0, 0, 0, right? Maps here, right? I believe, right? So, hash collision. So, not good. Why? Well, again, you say, okay, hash collisions in some ways are inevitable, right? Because you don't have access. This is what thing kind of got me first when I was thinking about it. I told you, we need a perfect hash. We want to avoid hash collisions. We can't really avoid them, right? We don't live in this perfect world where we know exactly what kind of keys we'll have, and coming up with a perfect hash function is impossible in practical terms, right? So instead, what we do is we want to do better than this, basically, right? This is a good starting point. We have a couple tricks up our sleeve. So what's one thing we can do, which seems silly, but what we can use, and this doesn't even affect the hash function, but something else. What can we use? We want to reduce these collisions. By the way, we'll deal in the second part of the lecture, or maybe this part of the lecture, we'll deal how to deal with collisions. What do we do when we have collision? There's two approaches after that. But for now, we want to reduce them. So, kind of interesting approach which you could use, which helps quite a bit actually. And really simple, tiny trick actually, right? So, in this particular case, what do we have a problem? Because this nice, powers of 2. So, powers 2, a really bad size for hash table, right? You don't want to have bad. This is because you have, in computer science, we have lots of powers of 2s, right? And if you have some hash table which is like, it's almost like a round number, right? Using a power of 2. So what do you use actually? So you use, yes, very good. We use a prime number for the hash table size. So instead of this, I'm going to remove it, right? So, right? Well, that's 255. That's also not a prime. So we use prime size. Well, we say okay, power 2 is prime. No, 256 is not prime. Prime size table. So I don't know offhand. 253 is 253 prime. Who can tell me? Quickly, 253. I don't think it's prime. What's called as prime? 257 is not. No. 253 is 8, right? That's 251 is a prime. Yeah. 251. Okay. So 251. So you do use 251. I'm trusting you that this is prime, right? So for what? For example, right? For example. So what does it mean? This means all these common collision possibilities, it will be spread out nicely, right? So of course it still leaves the problem if you, for some reason you have a data set which is this has 251, it has a specific property, right? Powers, 251 is an important number, you will still get more collisions than usual, right? Still. So yeah, so they're still going to use some tricks for this, right? To spread out the collisions. So again, the goal is again to spread out the collisions, right? Again, and then we come up to the second part, of course, is what happened? I said 100 keys, right? What do? We say have 300 keys. How about 300 keys? Right? Is that good? Actually, that's kind of bad, right? Your cache table, we obviously don't have enough room. Well, again, if you use something called open hashing, now we get to the hashing. What do we do with collisions? We have 300 keys. We know we're going to have collision, right? Pigeon, what's it called? Pigeon theorem, pigeon box, pigeon holing theorem, right? I'll put it up for you here. Right? Again, one of those obvious things, but kind of hard to prove. Pigeon holing theorem, pigeon holing theorem, right? Pigeon holing theorem, right? I forgot. Pigeonhole principle, right? Again, right? 10 pigeons, 9 holes. There's no way around it, right? We have the same problem here. So what can we do about it? Well, obviously, the approach, if we have more than, we could of course increase the keys, right? We can just basically expand, if you know, right? Then you have to rearrange. That's one approach, right? But then we sort of leave for another day. That's probably a valid approach. We'll see how to do that later. But one approach is maybe simpler is, what do we do with a collision? When we have a collision, well, we figure out some structure for collisions, basically, right? We just basically tack on n. So we tack on all 3 keys here, right? One, we use basically a linked list, basically, right? All of these 3 from here, right? Whatever the values is, right? We stack them on here. So for collisions, we tack them on here, basically, right? As a linked list. So that in a way, it solves probably the problem as far as technicality goes, right? You just stack on. But what's the problem? This means that in the worst case scenario, if we have a really bad collision function, let's say we have a collision function, we can make I'll make a get hash function would be get hash, return, let's say get hash, right? Would be, anything, value, right? And returns 0, right? Returns 0, right? So it's a hash function. It's a horrible hash function, right? Because it returns static. It's like the worst thing you could do, right? It returns 0. But this would be your first implementation of hash function. So yeah, so we would have what? Everything goes to the first box, right? All the pigeons go in the same box. And what do we end up with? Yeah, exactly. We end up with linked list performance. We basically regress to this, right? So that's how we get ON. So that's why we go N, because we get the worst of both worlds, right? We have a bad hash function, right? Basically, right? So sometimes again, very smart people who try to, if they figure out what kind of hash table somebody is using. If they know that, they can figure out some tricky way of providing some data, which sort of collides, right? Generates these collisions and basically squeeze everything into one box. So that's why a good hash function is worth its weight in gold. But again, where's my hash map here, right? No, that's our map here, right? So, but that leaves out another problem is, right? This function, this horrible, right? This horrible, bad hash function, get hash of value, get turn 0. It has one positive side. What's the positive side of this function? It's a function, let's say,
O1 insertion?
no, it's O1 general, right? It's extremely, well, first of all, your hash function should not have, it should be O1 for sure, right? Because the function itself, not ignore this, but this function itself, you just want a good hash function, right? So maybe I'll make a new slide. It's fast, exactly. It's very fast, and that's a great property, right? Because this is a challenge, is making a hash tables, hash maps, that balancing. Fast, but bad, but good, but slow. That's sort of like a balancing act, basically, right? So people find, there's still ongoing research, of course, still some improvements to be made. Of course, the basics are down, right? So yeah, so mod is good. Is in a way it has some really good properties because mod is like usually a CPU instruction, right? So this is pretty. It's fast, and so okay. So mod operations are sort of part of it, right? So it turns out there's some other operations. We'll see for hash functions, right? Design of hash functions. There are some other things which are easy to make for CPU. So we want to like square root, unless you have a CPU which specializes in square roots natively. I think maybe there might be, but still it's kind of expensive, right? So square roots usually not good. So log maybe, but maybe let's say integral value, right? A derivative? No, probably not. Something which involves multiple calculation steps, right? Especially if you say if there's some sort of, for large values it becomes expensive, right? If there's even something like maybe a bit of or something over 1, that would be really bad, right? So we want something fast, right? But we want something which spreads out the data, right? We want to spread out the data. We want to have it like have here, right? And we don't want them next to each other. So a lot of challenges, right? So let's look at some visualizations maybe, right? If this makes sense so far. Any questions so far? No. Okay. So let's look at this Let's look at open hashing, which is the simplest one. Right. Open hashing. This is what we talked about, right? So notice how many boxes, how many holes? No, 13. 13 is what kind of number? Prime. Exactly. Okay. So hash is going to be integer for now. Let's insert number 5. And I will put pause on it, right? So insert. Okay. Hash function, right? Simple, right? What can be simpler than that, right? Skip forward. Yeah. So now, let's put in 100, right? Insert 100. 9, you see? There we go. Now, let's put 200. Insert. So you can see now why it be bad. Oh, yeah, we got a collision. So this is easy way of solving it. We use a linked list for each box, right? You get a linked list, everybody gets a linked list, right? So it works, right? But now, of course, let's look for finding 5, right? We look. Do we have a key? Do we have a value, right? Let's put them. Let's put 213 again. Since I'm lazy, I'll put 213, right? Another collision, right? There we go, right? Okay, right. Now, so I'll want to find 5 because that's a crucial finding, or getting the value. Because again, remember this 5 right? Key is 5. There is a pointer to some data structure, which is what we are getting out. You know, maybe it could be integer, could be string, could be some object, complicated object. 5. So we find the box. We find the box. Okay, but we have to check now. This is where we have the performance penalty. 213. No, it's not it. That's not it. Aha, that's it. We got it. All right. Now, okay, we find it. But now let's look for 226. 226, right? It's obviously, you don't see it doesn't exist, but so how long will it take to check? Well, find. Again, the key, the index of our structure underneath is 5. And so I got to check. I have to check. 5. Keep going. Keep going. Keep going. And now finally, since the last element there's null, right, linked list, there's nothing else. Okay, didn't find it. So this means that element 226 is not found. Again. So yeah. So again, I talk about this. So when would you want to numerical integer as key? So when would you want a hash table? Of course, you have a very spread out. Your data is spread out all over the place, right? So how about minus 500, right? I don't know, right? Minus 500. I think, oh, I'm not allowed? Oh, I guess I'm not allowed my negatives. I thought I could. This one is integer, positive. I guess they kind of, this visualization tool is not really completely truthful. It's integer, but it's only unsigned integer. But okay. Let's do it. If it's at 500, 6. Okay, no problem, right? Right. Okay, so I'll say insert 2. Right, easy. So let's insert 15. Right. 2 again. So of course order, now you see of course order matters when you do this, right? Also, so deletion. So how would we delete, let's say 200? We don't want this anymore, right? Same approach. Well, delete 28, right? It doesn't exist, right? It looks 2, looks here, checks, is it here? So it's like find first, and if it don't find, don't do anything. But here, if I look for 200, right? Let's delete 200, or let's delete 5. Well, 200 is fine. Delete, we get the key, we know where we should look. So the mod does a lot of heavy lifting. This mod, simple mod function, which is very, which is basically CPU knows how to do reminder operations, right? It does a lot of heavy lifting, and we find it, and we got rid of it. You know, linked list operation. So pretty nice, I think, right? But again, unfortunately, so this is all very good. But that's the bad news is, of course, that in real life, it's rare you want to have a numerical keys as integers, rare, right? I don't know. I mean, sometimes you have big numbers, like IP addresses, maybe, right? That's example given in a you know, but like the example, like I have slides from 2001, I believe, right? It's one of them, right? And it's interesting, right? They mention IP addresses, right? 2002 data. And look at this here. They had 125 internet hosts, right? And growing every 20%. But by now we know what's happening with IP addresses. What's the story with IP4? IP4 takes what? 4 integers, right? 4 bytes. 4 bytes. Yeah, they're really running out, right? There's a brisk business now in companies that are selling rights. Even though technically you don't. Some organizations got more than they needed, right? They can make some pretty good money. And there's some countries that only have few IP addresses. In Latvia, we're pretty lucky. We have plenty. I think we have more than users. I think TET has at least 500,000 of them at least, or like 1 million at least, right? So we have plenty. We're in good shape, right? So we have a lot of problems. But going back to hash table, in this was when you had 125 million IP addresses, you actually actively being used, right? And then, well, you could think, okay, maybe a hash table makes sense, sort of, right? Because, you know, but now you have 4 billion, basically. You might as well actually plug it into some server with enough memory and put all 4 billion addresses there, right? So presence, you know, might as well use this, you know, make an array of 4 billion, basically, right? Because you always have them, almost all of them, right? So it's sort of it's kind of loses its point. But of course, IPv6, which is 6, right? I think 48 bytes. Let's see, 6 times 8, right? Yeah, 6 bytes. So 48 bits. That has much more space. You cannot store all of them, right? You need a hash table then, right? So yeah, so I could see IPv6. So IPv6 would be something to use, right? Let's see, IPv4, yeah, right here. Yeah, not Geeks for Geeks, but Juniper Networks is right, but Amazon, of course, also. More security, we don't care about security. Well, we care about security, but not in this regard, right? So, yeah, but availability, yeah, exhaustion, right? This was IPv6 was in 2000 actually proposed already. Yeah. Everybody knew, I mean, we knew this would happen, right? So, top level 31, all other spools, right? Africa still had some, I guess, right? Right, so the thing is, there are the things that makes worse, right? This is, 2 to the 32, right? 2 to 32. So, not all others are available. There was news like this year when they approved some testing addresses. There's some others like 168, 192, right? 01. Those are reserved for local networks, meaning they're not used publicly, right? They are fictitious addresses, right? Okay, but now, yeah. So others depletion, right? So it looks like there's some things you can see here. Exhaustion, right? Yeah, pretty bad. So, but IPv6, right? IPv6, right? Come on, 6, yeah. So how many addresses do we have here? You can do the math. How many? 3 to the 10 to the 38. So obviously you do not have as much memory as that, right? That's, I don't know, that's big number, right? Right. So actual number is a little bit smaller, but still. So you need hashing there. But in general, I can't really think of many usages of hashing when you have numbers so disparate. Like maybe if you have, I don't know, numbers from 0 to like million, but you only have like 100 items, then you might want to use hashing for numeric numbers, right? But mostly hashing is used for keys such as strings or maybe tuples, something like that. Maybe, multiple, something hashable, but something which has some meaning, semantic meaning usually, right? When let's say we have using, in JSON, for example, objects, right? Which are JSON objects are, of course, just hashes, basic hash tables, basically, right? In JavaScript, right? Dictionaries, right? So, so that leaves us a problem, which we'll have to explore in the second part of the lecture. But let's sketch out the problem, right? So what we do with strings. So what can we do? But again, sometimes not perfect. That's a start exactly. We just need some sort of. We will inevitably use the ASCII values or Unicode values, right? But then we'll have the problem of how do we hash things, right? We need simple, we need fast, but we also need it to be spread out. We want to minimize the collisions. Let's see. Let's do strings. And here it does not even let me choose the algorithm. Let's see what they use. Okay, so I have 13 boxes, and I'll put in RBS, right? What's going to happen? What do you think? Well, it's going to be like what you said. They're going to use some sort of ASCII representation. Let's look at our ASCII table first. ASCII table. Where's my ASCII table? Or friendly ASCII tables. All right. There we go. All right. So R is what? Capital R is 82. Okay. Well, let's see what happens. So there's going to be probably some. So the simple. Okay. Can you think of hash table for hashing function for strings? Like a simple one. So you said more obviously ASCII. So we get ASCII value, right? For if you had single letter keys, obviously get ASCII value or mode. But we have multiple multiple letters, multiple characters, what could we do?
Well, you can sum them
We
up
could, yeah.
or multiply them.
Yeah, I was gonna ask. I was asking for sum it up because that's the simplest thing which seems. But of course, we'll see this is not the best way to do it, right? But if it's simple and it sort of works, right? It's a start. It's a start, right? So let's do this. I think it's going to use something more complicated, right? Before the break, we can see the idea. Hashing RBS, right? So obviously we get the bit value, right? Here, right? From end actually, right? Okay, S. So S is what? S is 83. Oh yeah, RBS, yeah, S, right? Okay. So what's the remainder divided by 378? 5, right? I think 5, right? 78 times 6. No, yeah. Remainder is 5, I believe. But let's see. Okay. But we don't get that actually yet. So it's actually going to add up something here. Let's see. It's going to do a byte shift, shift left, basically, right? To add the other next one, right? Oh, XOR operation. What's XOR? Exclusive OR, right? So what has a property? You have to have it's true only if one of them is true, but not both, right? So again, you might be asking, why do you use this XOR? Why is XOR used? Well, again, first of all, because it's extremely fast. CPUs are good at doing XORs, right? It's like built into their blood, right? So, but it also has some good properties also. So, we do XOR, right? With this part here, right? And see on, then, right? B, we look at B, right? B, right? We add that. I think we add it. Yeah, we add it, right? Do XOR now. Again, we push, right? And again, it seems like the XOR here is kind of like not needed. We can skip it basically, right? And we add R finally, right? And you see it's gonna move around, right? There's gonna be, yeah, this one here, one. We have some duplicates here, right? So again, so this is not a simple addition, right? This is actually like we raise it to the power. So shifting is like raising to the power of 2, right? We raise to the power. So basically it means is we want to spread out the information. Basically, if you have R and BS, right? We don't want them to be squeezed into this tiny box of, these small numbers. We kind of spread out. Again, so now let's see if the last step should be same what you've taught. So 22,386, basically, right? Okay, just number, but the last step is exactly what we expected. Oh, in this case, 0. So RBS goes into box 0, right? Very nice. So let's see if we can get another box 0, right? So how about, let's make a hash collision. 78 is N. Let's do that. Capital N. I think it's going to work. I think, unless there's something else, right? N. I think that's it, right? Yeah. 78. Yep, we got hash collision, right? So we got N is hash collision. But yeah, so if I do dumplings, let's do dumplings. Dumplings, right? That's probably going to be interesting. Right, dumplings. So we have 4. Then we'll take a break. So D, right? That's for D. No, G. Sorry, G. Small G, right? XOR. For now, XOR doesn't make any sense, but we will see this XOR. Right? We keep moving. Right? N. Right? So eventually, just imagine you have big text. Your hash key is like maybe a half page of American independence, declaration. It could be, I don't know. But so then eventually, of course, the bits, we don't have enough room, right? It will start over, So this XORing sort of like will ensure that we still have enough sort of like, how should I say, spread outness, I would say, right? So I'll skip over these, right? You can see we adding. Yeah, this XOR 00 never does anything actually at this stage, but now, right, we keep moving. So for each letter, how much power do we raise? 4? Do we multiply by 16? Let's see how many bits. I think 16 because 4 bits, I think. Oh, that's interesting actually. So now we get. So yeah, okay. So finally we get to the point of the XOR. So now. This part here, right, which we cut off, moves here, right? It used to be zeros, right? So we use that extra information. So again, what does it accomplish? Well, it's sort of like a mix-up that this text still has some relevance, meaning the text which seems like it was lost, right? So this makes it that it does have some, it provides some input basically, right? Otherwise, what will happen is that dump and dumplings will have same hash value basically, right? And in this case, right, it will not, right? So that's what we get with these XOR variations, right? And again, it's deterministic, which is good, of course, right? And finally, again, we'll have this the XOR, right? You see it move the XOR here. And finally, we have this addition, and now we are going to have this huge value. I guess it's 30, it's like 32-bit value, I guess, right? And we divide by 13, which is 7, and we are now dumplings here, right? So let's take a break, 15 minutes, right? And we'll see if dump is same value.